My name is Jordan University. This is Nathaniel and Kobe. We're part of the Honeybee wireless environmental monitoring system team. I'm going to hand it off to Kobe to give you guys an intro and overview.
Hey everybody, I'm Colby Henderson, computer engineer. I worked on the wireless and the water array for our systems, so let me get into it. We did the Honeybee project. We're continuing on last year's senior design project. They actually had a monitoring system in the hive with a camera and some temperature probes, stuff like that. So what our job was, given by Dr. Fortier, was to continue on that by measuring parameters of air, water, and soil for bees in that area. So ours was more of a proof of concept to continue on further. So there's some grad students who are working on some more advanced sensors as well to kind of keep pushing the project along. All right, so these are our main customer requirements here. Device must last at least 1 month in the field. Detect if water is safe for consumption by bees. Ensure the soil is safe for plant growth and therefore bees. Ensure the air quality in the environment is safe for bees. Device must be modular, weatherproof, and watertight. Product must also be able to wirelessly receive and transmit data. Another thing I forgot to mention, so this is all revolving around colony collapse syndrome. There are systems out there that monitor honey production, stuff like this. This was strictly to try to monitor an event where a whole colony dies off. The engineering requirements, just kind of going into the first one, device must last at least one month in the field. This was a power constraint we really had to kind of pay attention to. So self-operation product shall be capable of operating in the field for at least 1 month without user input. So we really needed to have this remote and something that could just kind of live there until someone went to either collect data or put a new battery in. Product shall be capable of operation without interruption due to loss of power for at least a month. Again, the battery thing, the power constraint. Also, a size constraint. We don't want this huge beast out in a pond. No one's really want that. Remote control. So, product shall be capable of accepting user input as operation controls. Next one, detect if water is safe for consumption by bees. The project really started with us with the concept that we want to come up with some triggers and some ideas of what would be toxic to bees, kind of going on to a biological. We're kind of computer engineers, so it was kind of a challenge to find exact sensors for our use. So what we did is we put pH sensors and we put ppm detection into it, so we could kind of come up with some triggers. Let's say there's a toxic pollutant put into the water, some type of arrangement of data would kind of signify that. So it also goes on, this is for the soil, it's kind of the same idea. So we kind of picked some sensors that we decided would be safe for even human consumption. So just kind of going through a few of these. The temperature, measure hydration and moisture in the soil. And we also did the light level. We figured since plants are, where bees are getting most of their food source, we want to kind of see wherever we deploy this, what's the light that the vegetation is getting. And ensure so this is for temperature and air quality. So again, kind of going through some standard environmental observations. It must be modular, weatherproof, and watertight. So this is going to be out in the field. Actually, the place where we planned on putting it. If you come into Ring Road, there's a small pond. Dr. Fortier has observed the bees kind of collect water from there, and that seems to be a source of food and water for them. So Nathan has kind of worked on our enclosure and making sure that we used 3D printing to kind of get this done and make sure everything was really watertight. And onto the wireless requirements. So we had a few options here. We ended up landing on Zigbee. A few other teams use Zigbee, no pun intended. The reason for that is it's really low power, and it also met the requirement of broadcasting from the graduate lab to the Dept pond, and then there's also another hive that's kind of near the engineering parking lot. Alright, these are some of the constraints and standards. Device must last 1 month. Battery should be small enough to ensure manageable weight. Again, we don't want this big bulky thing out in the field. Water quality, soil, and air. Like I said, we're going to have some more advanced sensors, not us personally, but when this project kind of progresses in later years, there will be some sensors that are specifically made for this type of detection. And that's also part of this proof of concept, is having all these different arrays using I²C. We could really throw anything we wanted into. And just going over the FCC Code of Federal Regulations, Zigbee is on a 2.4 gigahertz band, so it's pretty open. I don't think there's any, there wouldn't be any real issues we'd run into there. All right, and I'll pass this over to Johnny.
All right, so this diagram is depicting a high-level system diagram of our device. It's meant to be easily interpretable. So basically it's showing a central beehive here, and the radius distance around that. We're going to have our device here monitoring the environment, and we also have a remote computer somewhat distant away from the environment, and the device will transmit the data collected from the sensor arrays. So here's a control state diagram. It's kind of hard to read, but so basically on startup, the connected sensor arrays will be enabled and data will be collected. The device will attempt to transmit the data, and control commands and sensor selection commands will be monitored throughout. So some sort of command where the user would want to type in, collect, and right then and there the data will get transmitted to them, or some sort of sleep command where they can have the device sleep for a certain amount of time. And after this, the device will then check again if any new sensor array has been connected, and the data will be gathered through those arrays. So in designing our products, we had to look at 2 separate array designs. So we were contemplating between a simple array and a detailed array. A more simple array would, the benefit of that would be low power, cost efficient, it's a cheap proof of concept. Some weaknesses are that it's a less amount of data to determine p health, which in this case, because it's proof of concept, it's not really that big of a deal. For a detailed array, the strengths and benefits are that there's more data to be read in, better for use in monitoring the environment. There's tons of parameters that you can gather data from. Weaknesses, high cost, and then again, less relevant sensor data for the cost. It's not really a good benefit. So we made a Pew matrix here to decide on the array design. So we gave weights to cost here, to weight for cost. For 5 days, the proof of concept was a huge thing for us, so that get a weight of 3. And then +1 means it's desirable, -1 means it's not desirable. So we decided on with the simple array because of the cost and the ability to provide for proof of concept. So here's a technical design. This is just the main device connected to the air array here. So the main characteristics of this is that we have a 320p microprocessor in our case. We're using Arduino Uno. We're going to be utilizing the I²C protocol just because of simplicity and the few amount of wires that it takes. But when we use sensors that are analog, we're going to be, we plan to use an 18x85. So that would act as a slave to the microcontroller, and it would control the sensor, collect data from that, and then would send data from the tiny to the microprocessor via I²C. And I'm going to pass it off to Nathan to talk about the conclusion.
We were choosing between 3D printing or CNC milling for our enclosures. We were thinking that CNC milling would start out with a solid block and be easier to create a waterproof object. But due to limitations in time and last-minute changes in dimensions, we ended up leaning toward 3D printing for our prototypes. 3D printing was inexpensive. It created fast, easy prototypes, but it wasn't quite the level of waterproof we wanted for our water sensor. So for our water array and our soil array, we purchased 2 enclosures. All of the enclosures used O-rings, gaskets, and waterproof connectors. This here is a picture of our air sensor enclosure. It was designed on SolidWorks. Our water and soil array are seen here. They used polycarbonate cases from Polyfix. They met the IP66 and IP67 requirements for waterproofing. We cut out, we create cutouts for the plugs and sensors using a laser cutter for precision and simplicity. This is a picture of our main assembly. Our main assembly has 3 holes for the plugs to connect to the other 3 arrays. Originally, we were to have a soil sensor as well. RTV and epoxy were used to seal the covers and seal around components. All the edges were filleted to create a more uniform wall thickness and less stress concentrations. They were all manufactured in 3D printing. Originally, we had created 2 smaller enclosures, and because of our battery life requirements, we had to create a larger enclosure to fit our new battery. Since we were trying to seal all of these from the weather and from the water, it was also becoming airtight. And so to get accurate readings for our air sensor, we used a waterproof air vent. The air vent allowed the pressure to be equal internally as the external temperature, and it helped the seals to last longer and the components to last longer as well by providing ventilation and reducing the possible risk of condensation. All the connectors we used were 4-pin waterproof connectors we purchased. We created our own 4-pin cables using automotive wiring and shrink wrap. We have covers for all the sensors, for all the plugs, so that when a sensor is not used, the connections will be covered up and also be watertight.
All right, so here are some of our test plans here. You can see on the right side over here in green, passed, red, unable to test or they failed. So we had to test if the device was waterproof, because obviously this is going to be in the environment, and the water array will actually be in the enclosure sitting on, and it has to be watertight or weatherproof. So that passed our test. We took one of the enclosures and made them run under a sink for an extended period of time, and it kept the water up. So 1 month of uninterrupted operation. That was one of our tests that we could not perform because of time restrictions. We planned on just using external battery and just seeing how long that could last with it. Wirelessly transmitting and wirelessly receiving data. We were able to wirelessly transmit data from the device, but we were unable to wirelessly receive data at the device standpoint. We weren't able to send data from the server to the device to send sensor selection commands and whatnot. Collect data from the 3 arrays. We only had 2 working arrays, but so that's why I gave us a pass-fail, because we can't test it with 3 arrays, but it works with 0 arrays and there's nothing plugged into it. It says, nothing connected. When you plug one array in, the server will tell you this array is connected. It'll start collecting data. You plug in another one, and you have all the data coming in. Data is easily interpretable. Code did a good job in writing a simple Python script we'll get into a little later. Basically, it reads in serial data over each radios and imports it to a text file. Arrays are modular. Like I said, we collected data from no arrays connected, 1 array connected, 2 arrays connected. So they are modular. They do connect and disconnect from our main device. For the air sensor, we're able to test temperature, get an accurate reading of temperature. We weren't able to test humidity. We don't have a sensor to do that. We're able to test pressure, and then for water, we're also unable to do the water temperature one, but we did end up implementing a water pH sensor that can detect the acidity level of water. And due to unforeseen circumstances, we were unable to complete the soil array. So here's our planned schedule. So again, like everybody said, time management is a big thing. We manage our time poorly. We had some things happen to our group that we could not control. But yeah, it's go ahead and hand it off to Colby now to finish off.
Alright, so our lessons learned, plan for the worst, so we really didn't see a lot of the curveballs that got thrown at us this year, so we probably should have not planned for a smooth sail. I've heard that a few times. Start design as early as possible, so we did plan on having PCBs for this made. We had those sent off, but those also kind of got lost in the issues. Review inventory of components and their ordering status on a weekly basis to ensure completion of the product within the designated time frame. So a lot of some of the parts that we had towards the end when we're putting them all together, we had lost some sensors, so we should have been doing an inventory every week of integral things that were part of our project. Summary, so we actually did meet most of the customer requirements besides being able to send data back to the device itself. There is no soil array and no sensor selection command sent from the server. Our design uses XP radios, which can be meshed with last year's product. So we used S3B Pro Zigbee radios. That's really important because if you use anything a different standard, the radios can't mesh correctly. So there's you could say a server implemented outside of the graduate lab that was communicating with last year's project. So the end goal of this is to really get everything meshed together and then eventually have that whole radius monitoring the system. And so here we just have a few pictures of our array. So the water array we actually had to use some sealant on, so we couldn't open it up to display it at our table. But this is just the internals. We have a pH sensor and then a turbidity sensor. There's an O-ring, kind of like Nate talked about. And we also have a blue piece, a blue 3D print piece that kind of holds pressure on that. This is the air array and that air gasket that Nate was also talking about. So obviously we wouldn't be reading any good data if it was watertight and it's the same stale air that's sitting in there. And this is just the two arrays with our main box. The one on the right is the main box with the Uno and our Zigbee node, as well as the two other water on the left and then air in the middle. And you can kind of see those connectors. So when it's not being used, there's three connectors just like those blue ones on the top of the box. You just open them up and the server will detect a new array. This is just the raw data stream coming over the serial connection. So this is what the server sees, just what it's reading in the data, and then we decode it, do UTF-8. So we had a broader plan for this. I really wanted to use JSON to kind of develop a bigger backend, using Azure, or there's a few .io free websites where you can kind of host these cloud-based sensor selection things. They use it a lot in smart home systems. But unfortunately, we couldn't get there. But in our report and some of the documentation, we're going to be handing over to the next team. That will be something we'll be recommending. So future work, I kind of just talked about it. Dr. Fortier has grad students working on their own sensor arrays. We were just talking inside. They're very specific to monitoring toxins that are in the water. That was something, a big problem we had. So we were eventually going to get an warp sensor with a pH sensor and a few other ones to kind of develop a system that would say something toxic was in the water. However, we really couldn't figure out a way to say exactly what was in the water, just that something was introduced. So that's when we pivoted and we moved more to a proof of concept. So at the end of this, that's when we're going to kind of give our platform over. The PCB design is still to be completed. Hopefully next year's team can get a more final PCB printed and implement user interface so they can choose when to receive data. This would be something on the back end using the JSON data. Any questions?